Okay, so let's talk about the triangulation of orbifold. So in general, smooth orbifold has a smooth topological stratification and a smooth triangulation, so that each open cell is contained in a single stellum. A smooth topological stratification satisfying certain weak conditions satisfy triangulation. So we will show that the stratification of an orbifold by orbit type satisfy this condition. We will mainly follow the book, this book by Verona, also the article by Mordicic and Pronk here. Okay, so probably we won't be able to show this, but we'll just state the result. Okay. So basically, we'll do the stratification. So first we will explain what the stratification is. So let's say X and Y be two subsets of the topological space X with empty intersection. If X is in the closure of Y, then we write X is smaller than Y. We say that X is smaller than equal to Y if X is equal to Y or X is less than Y. A face of a topological space A is a cross subset of A with a smooth embedding FB from UB to B times R for R plus for a neighborhood UB of B sending B to B times 0. So here, of course, I mean the R plus ones containing so the positive or number plus the 0 here. And so we need faces because we will be studying orbifolds with boundary. So essentially these are the boundaries here. And FB and UB are said to be the color or the color neighborhood and the color neighborhood. And we write FB to be we can write FB to be PB times comma RB, where PB is the projection to B and RB is the so the sort of distance function from B here. So these are the smooth functions. Okay, so usually they will require to be the smooth functions, but of course we haven't really defined the smooth structure here. So Hausdorff locally compact and paracompact space with countable basis is said to be a nice space. Let A be a nice topological space and X subset Y to be locally closed set. A tube Tx of X is a neighborhood of X with the retraction pi x Tx to X and the function so rho x Tx goes to R such that rho x inverse 0 is X. Okay. So these are really not tube in the nice topological sense, but just some data we will have for some neighborhood. Okay, so given a positive valued function epsilon delta going from X to R with epsilon from 0 between 0 and delta, so we define X times open neighbor epsilon delta to be X T, where epsilon X is T is between epsilon X and delta X. So it's a sort of sort of fiber bundle over X. So with the obvious extension to closed interval case, you can also do the closed interval or half open interval, or you could have a closeness here or closeness here. Okay. So those are well-defined sets. So let's define T epsilon X to be A in Tx, where rho x is less than epsilon of pi x A, for the function epsilon going to R plus, where epsilon is less than 0. So if X is in U for inside A for an open U, then T epsilon X is in U for some epsilon. So pi x rho x from Tx epsilon X is a proper map into X times 0 epsilon, where this is as defined above by choosing a sufficiently small epsilon. So we will only look at the cases where this holds for Tx. So for tube to hold, you need this condition. So abstract stratification A consists of a nice space A and the locally finite family A of locally close connected subsets A prime of A. So these are called strata. So singular is a stratum. So that A is a disjoint union of members of A, where members are smooth manifolds. Okay, so they have smooth structures, and family of tubes of the strata. So you will always have these tubes with pi x and ox. Okay, so of course these satisfy the previous properties, and the family of closed subset A star of A called faces satisfying the Python properties. So these faces will be play the role of the boundary of this A. So it's some sort of generalized boundary. So, for example, if you have a polytope, then the side of the faces of the polytope will be the faces here. Okay, so they correspond to that sense. So for manifold with corners, they will have a natural notion of faces. So if x and y are in A with x intersects here, y is not empty, then we have x less than y. So this is a property you need to require. And for any face AI in A star, there exists an open neighborhood UAI and the homeomorphism FA from UAI to AI times R plus onto an open set, so that the points on AI goes to A0, and for any x in A, if these x intersect AI is not empty, then FA x intersect UA goes to x intersect UA AI times R plus for a color FA of AI, because AI as always is a color. And we define P8 to be UAI going to AI, and RAI going to UAI to R plus, and then the FA will satisfy this relation, okay? Because these are homeomorphism, so it will satisfy this property. So each stratum is a manifold with faces. So xi, which is xi intersect AI. AI is in AI star with colors. So manifold with faces means is a manifold with corner, and the faces will be these. Okay, so faces means that there is these functions. So fxi, which is a restriction of fai, restricted x intersect uai, and uxi goes to xi times r plus as a homeomorphism to its image. Whenever x AI is not empty, x intersect AI is not empty. Also, for x in A, AI is in A star, so we have pi x inverse xi is AI intersect tx, and fxi intersect pi x is circle pi x is going to be pi x. So I don't want to so pi x restricted to tx intersect AI times identity Ri circle fai. So it satisfies certain compatibility condition from xi to fi. So that's all what it is. Also, there are other compatibility conditions. If you have some other elements of x in A and then y in A, and then that kind of thing. So I don't want to really go through with this, but there's this compatibility between the elements of A and these their tubes and that kind of thing. So I don't want to really go through it, but please look at the book by Verona. And so for any x in A, AI in A star, we have rho x equal to rho x circle PAI in the neighborhood of AI. So again, this is a compatibility condition between the element of A and AI star and so on. So we need this compatibility, because otherwise it doesn't make any sense. So so dimension of a stratum is a dimension as a manifold, and if x is in the closure of y for strata x and y, then the dimension of x is strictly less than that of y. Of course, this needs a proof, but we will not give you the proof. So it's in Verona. And the depth of a stratified space is in the maximal cardinality of collections of form x1 to xn of strata xi satisfying the xi is less than xi plus 1 for all I equal to 1 to n minus 1. So the dimension strictly increase in a chain, okay? So in the chain like this, and the maximal dimension of the strata are open manifold, so you have nothing containing it like this, where the tubes are identical with themselves. So this is the maximal dimension, so you don't have any other tubes, okay, unless it is itself. Okay. So stratification has a finite depth if the maximal dimension of all the strata are finite. So with some uniform bind. Okay. So let's go to the triangulation. So triangulation of a topological space A consists of pair K phi, where K is a countable locally finite simplicial complex, and phi going from the topological space of K go to A is a geometric. So K bar, this is a geometric realization of K. So this is a homeomorphism. So that's what we mean by triangulation. So relative manifold with corners is a pair of topological space V delta V, so that V delta is a cross subset of V, and then if you remove this delta V, it is a manifold with corners. Okay. So a triangulation K phi of a relative manifold V delta V is a smooth if delta K contains a subcomplex delta K, so that phi delta K goes to delta V, and for any simplex delta of K, the restriction of phi to delta minus sigma, the space of sigma minus space of delta K is smooth. And for each of these points, you have a differential at phi at x is injective, so you have to look at some simplex containing it, and then you have to consider the differential there for every simplex containing it. So the theorem of Verona is that if X is a nice space and A is an abstract stratification of X of finite depth, then there exists a smooth triangulation of A. So we go to triangulation of orbifolds. So we need a slight generalization of orbifolds with boundary. So recall that R plus is a space of non-negative real numbers, and R n plus is the Cartesian product of all these. Then we define orbifolds with corner as an orbifold with following properties. So each point has a model U G psi, where U is an open subset of R n plus, and G is a finite group acting on it that acts on each face of R n plus that U meets. So this means that each face of this space, so this has a natural structure, combinatorial structure, and that they will have to be preserved under this group action. So we want to switch faces. So in the manifold cases, we define the co-rank of point as a co-rank in the model. So any point here will have some co-rank, which means so there's some strata that contains this point in this. So this has a natural stratification, and which is just so the maximal dimension of the least subspace, which is a product of these contained in here, and they will have a co-dimension, so that will be the co-rank. So we define the face as a subset of delta omega as a closure of a component of set of co-rank 1 in delta O, and it is delta O as required to be the face of underlying space of O also. So if you have an orbifold with the corners, okay, then the face is as a subset with the co-rank 1, so it will just be modeled on Rn minus 1 times some R here. Okay, so that will be the faces of Rn plus here. So the lemma is that given an orbifold with corners, we can give a Riemannian metric and O so that the faces are totally geodesic and they are perpendicular to each other when they meet at a codimension 2 subspaces. And each stratum of X of O is a totally geodesic manifold with faces in partial O and is and perpendicular to faces in partial O, and is neatly embedded with color about X intersect F for each face F of partial O. So here neatly embedded, that it means that it's kind of perpendicular. So so I'm not going to say too much about that, but please read my book here. So so these are just a fact that you can always do everything locally. So you can just use a partition unity to make these happen, and that's the basic idea here. And the theorem is that if n is a orbifold with n orbifold with corner, each singularity x of an orbifold x with a local group gx always lies in a submanifold of points whose local groups are locally conjugate to gx. So of course gx could be trivial, then it will be in the maximal dimensional set. Then the collection of such submanifolds with non-singular components forms an abstract stratification of the underlying space of the orbifold with corner. So therefore, O with the stratification is, of course, smoothly triangulated by the previous results of Verona. So here, so we will have to. So the basic idea is to use this previous lemma to show that this stratification set is a real stratification, and then we'll have to use the theory of Verona to complete this. So this ends the lecture here.